we've discussed concepts like the first derivative test, the second derivative test, and we've learned about critical points, and we know other pieces about functions like intercepts that we've learned before, but one of the final capstone pieces about understanding function behavior using calculus is the idea of limits at infinity. And what that means is, what we're trying to figure out is this idea of end behavior. So usually when you sketch a graph, you pick some sort of window, right? Some minimum x value, some sort of maximum x, minimum y, max y. You plot a bunch of points, and that's kind of your window. But you may want to figure out if this function, what happens as those x values get really large, either in the negative case or in the positive case. And you want to know, okay, well, what's going to happen to this function eventually? Is it going to just shoot off to infinity, or is it actually going to level off somehow? Or in other cases, like in a sine wave, it never levels off, but it's stable. It never goes above positive 1 or negative 1. It just stays that way in perpetuity. So that's not that interesting, but things that level off are very interesting because those are what are called asymptotically stable functions. So that means that as time goes on, they really level out. Think of it sort of like throwing a rock in the water, and it ripples and ripples, but eventually those ripples go away and you have a flat surface again of the water. But anyway, the way we do this is by investigating two limits. And this is the limit as x approaches infinity and as x approaches negative infinity of the function. And what does that mean? Well, really what we're trying to do is analyze what happens when function inputs get very, very large. And really the kind of the four major limits of interest that we use and manipulate are these four. The idea that as x goes to infinity, x itself goes to infinity. Wow, that's not exactly a revelation there. And as x goes to negative infinity, the function x goes to negative infinity. Again, these are very trivial limits, but they're going to come into play because if x goes to infinity, then x squared is going to go to infinity because, both of those are going to go off. Now, x squared would go to positive infinity because the negatives would cancel, but x cubed is going to go to negative infinity. X to the fifth is going to go to negative infinity. So we see that polynomials tend to follow this type of behavior. And then similarly, what we have is if we end up dividing by x, if x gets really large, well then 1 over a big number is actually a small number. So, again, if it's x squared or x cubed, this just drives down to 0. And you find that's true in the case of negative infinity because 1 over a large negative number is also going to tend towards 0. It's just going to tend to it from the left as opposed to tend to it from the right. Right? These are going to positively approach 0. These are going to negatively approach 0. So anyway, if we want to look at a simple function here, let's take a look at this. 3x squared over x squared plus 1. Now we could rewrite this as this function, and I'm going to discuss why we would rewrite that in a minute. You would have to use a little bit of algebraic cleverness, but in general you can rewrite it as that. Now anyway, if we were to take a table of values and plug in 0 into the function, we would get 0 as the output. But if we plugged in 1, we would get a 3 on top, we get 1 plus 1, we get a 2 on the bottom. If we plugged in a 10, we'd get 300 over 101. So this is 3 halves, like 1 1/2, but this is really close to 3. This is even closer to 3, right? That's just this little bitty remainder of 1 over here. But you find as we go towards positive infinity, you're always going to have that little tail 1. Even here we actually have a tail 1. We have 3 over 1 plus 1, but it sums up to 2. As we keep going towards infinity, we're going to find we hit this limit of 3. And similarly, if we go backwards with negative 1, negative 10, negative 100, you're going to get the same function outputs, and you're going to find those also go to negative 3. So we can use that information along with the fact that we know we could also do the first derivative test. We could find the critical points, things like that. You're going to find a critical point at 0, 0 here. And you could use that to sort of start to shape your understanding of what the graph looks like. So what we see is that the function is going to be decreasing, it's going to hit 0, and it's going to be increasing. And then it's going to be concave down, it's going to hit an inflection point, it's going to become concave up, it's going to hit another inflection point and become concave down. All the while, it's trending towards this positive 3. It's trending towards this positive 3. And the reason why I say that it can be helpful to rewrite it in this form is if you look at just this and you start to plug in a really big number. Well, if I get a really big number, this whole denominator gets really, really large, but the numerator stays static, so it just drives the value down, right? As this becomes 101 on the bottom, that's a small number. It becomes 1,000,001 on the bottom, it's an even smaller number. As it becomes 1,000,000,001 on the bottom, it becomes an increasingly small number. So what you're seeing is you'll see this vanish as x approaches infinity, and the only thing that will remain is that 3. And that's what you're basically seeing here, is that those values get large. That sort of remainder term vanishes. It dominates here, but it vanishes as x gets large, and that's kind of that's the general approach. And we'll do some more examples about limits and infinity and learn some tricks about how to manipulate functions to make these limits more understandable.